Hello, and welcome to another TA Tech Tip. In this tech tip, we will discuss the parallel plate geometry on the TA Instruments HRx series of rheometers and show you how to set up and run this experiment on a soft solid. The parallel plate geometry is one of the most common configurations utilized in rheology. On HRx rheometers, this consists of an upper movable plate and a bottom stationary plate. As discussed in our HRx overview, the upper geometry is attached to the combined motor and transducer movable head, while the lower base serves as a temperature control unit. This geometry can be used to test a wide range of materials from lower viscosity liquids to soft solids. This configuration can be used to obtain a complete rheological profile, including flow, viscoelasticity, and time-dependent properties of these materials. There are several reasons to use parallel plates as opposed to similar configurations such as cone and plate. These reasons include a variable gap, wide range of plate diameters, and roughened surface texture. The variable gap is beneficial for non-isothermal tests or experiments where the material expands or contracts. It is also useful for samples containing particles, as the gap should meet the condition of being 10 times the largest particle size. Cone and plates require a constant gap, and typically a small gap throughout the experiment. In addition, TA offers parallel plates from 8 to 60 millimeters in diameter. The diameter selection, along with a variable gap, allows simple tuning of the strain, shear rate, and stress that can be applied to the sample, as these are proportional to the radius of the plate and/or the gap used in a given experiment. Parallel plates can also have roughened surfaces, which are beneficial when testing samples prone to slip. An additional tech tip is available on how to identify and avoid slip for parallel plate experiments. In this experiment, we want to test the linear viscoelastic properties of a soft solid material that is comparable to toothpaste at an isothermal temperature. The first step is to determine what upper movable plate to use. For this type of material, a 40 millimeter plate with a sandblasted surface is appropriate. As a rule, smaller plates are used for stiffer or higher viscosity materials, while larger diameter plates are used for weakly structured or low viscosity materials. Next, the environmental system is chosen based on the desired experiment. For isothermal parallel plate experiments, a common setup is the use of an advanced Peltier plate. This plate has rapid, accurate, and precise control over a wide temperature range, along with allowing quick change plates of different surface finishes to be used as the bottom stationary parallel plate. For samples prone to slip, the use of a top and bottom plate with a roughened finish maximizes the reduction in slippage. Now that the configuration is chosen, the instrument can be configured. First, the Smart Swap button on the instrument touchpad is pressed to unlock the magnet, and the advanced Peltier plate is placed on the base of the instrument. The fluid circulator tubing is then connected to the instrument, and the circulator is turned on. Following this, the Peltier plug is inserted into the bottom right port of the instrument. Once plugged in, the instrument registers the Peltier plate as the temperature control system. The bottom quick change plate can then be placed on the surface of the advanced Peltier plate and locked in place with the quick change plate holder. Once the bottom Peltier plate is configured, the upper parallel plate can be attached to the upper draw rod, and the Smart Swap option in Trio software can be used to identify the geometry by its barcode. Next, the geometry calibrations of inertia, friction, and rotational mapping can be performed. An additional tech tip details these calibrations. After the calibrations are performed, the isothermal temperature for the experiment can be set in the Trio software or from the instrument touchscreen. After the temperature is equilibrated at the desired temperature, the upper geometry can be lowered to a few inches above the bottom plate surface. The gap can then be zeroed from the instrument touchpad. For isothermal experiments, it is always recommended to zero the gap at the isothermal temperature the experiment will be performed at. Once the gap is zeroed, the upper geometry can be raised to the loading gap in Trios or be manually raised to a comfortable height for sample loading. The sample is then placed directly on the center of the bottom Peltier plate. The Trio software provides a minimum sample volume value based upon the geometry configuration to guide sample amount when loading. For limited sample situations, the exact volume can be used, but if excess sample can be used, it is recommended to add slightly more than needed and use trimming to ensure a proper gap fill. After sample loading, the upper geometry is lowered to the trim gap, which is typically 5% of the geometry gap in the Trio software, or by pressing the trim gap button on the instrument touchpad. Once at the trim gap, the bearing can be locked from the touchpad to prevent the upper geometry from spinning during trimming. The sample is then trimmed and the upper geometry is lowered to the geometry or experiment gap from the Trio software. Visually examine the edges of the geometry to ensure the gap is completely filled but not spreading beyond the gap. A very slight bulge of sample at the edge when the experiment gap is set can be expected. The programmed experiment can then be started from the experiments window in the Trio software by pressing the green start icon. When the experiment is active, the instrument touchscreen and Trio software will say running. Once complete, this will change to idle. After the experiment, the upper geometry can be raised manually with the touchpad buttons or by selecting Raise to Loading Gap from the Trio software. The geometries can then be wiped clean for a new experiment. In this tech tip, we discussed the parallel plate geometry on the TA Instruments HRx Rheometers and ran an experiment to test a soft solid with this configuration. Please stay tuned for more helpful tips from TA Instruments, and thank you for your interest.